Hi everyone, let us discuss the proof of Rolle's theorem. Okay, so let us try to understand the statement of Rolle's theorem first, then we will discuss its proof. If we have a function f defined on closed interval ab, what will I do? I will draw the diagram simultaneously so you can easily understand its meaning. Okay, so we have a function f, I am drawing the graph of it. Okay, here we have a closed interval ab, the function f is defined on this closed interval ab. The first condition is f is continuous on closed interval AB. That means graph must be continuous without any break. Okay, so let me show it here. Suppose the graph of function is like this without any break. First condition is satisfied. Second is function is differentiable on open interval AB. Differentiable, that means there should not be any corner point. Okay, it has no any corner point. Graph is smooth, so that's why function is differentiable on open interval AB. Third and last condition is f of a is equal to f of b. That means whatever the value of f at a should be equal to the value of f at b. So that means at a function has a value f of a here, right? You can easily see. So at point b also the function should have the same value. Okay, I have drawn the graph like this such that the function has the same value at point b also. So you can say f of a is equal to f of b. So if any function satisfies all these three conditions, then we can say there is some point C belongs to open interval AB. I am saying open interval, okay, AB, such that f dash of C is equal to 0. So what is meaning of it? Dash means derivative, you know, and derivative means slope of tangent. Getting? So there exists some point C such that at that point the slope of tangent must be 0. That means that tangent must be parallel to x-axis. Okay, so this theorem says that there is some point C. There is some point C in this open interval AB such that at that point C the function has a tangent. Okay, so that curve has a tangent which is parallel to x-axis. That means its slope is 0. That means derivative of f at C is 0. Okay, so this is a geometrical meaning of it. So let us start to prove this theorem. Okay, we have these three statements and with the help of that we have to prove there exists some point C belongs to open interval AB such that f dash of C is equal to 0. So let us start the proof. Okay, yes. Okay, so let me write a given information. We have f is continuous on closed interval AB. So you know that if you have any real valued function, continuous real valued function defined on closed interval AB, then then on any closed interval, then function attains its maximum value and its minimum value. So therefore let me write here, therefore implies f attains its maximum value, we will call it as capital M, and minimum value we will call it as small m. Okay, on closed interval AB. That means function attains its maximum value and minimum value. Maximum value we are denoting it by capital M, minimum value we are denoting by small m. Okay, so now there will be two cases. Either capital M is equal to small m, and the second case is obviously capital M is not equal to small m. So let us discuss the first case. Case 1, that is capital M is equal to small m. Capital M, that means a maximum value, and small m, that means a minimum value. Here we are saying both of them are equal. Maximum is equal to minimum. That means function must be a constant function. Okay, so let me write here, implies f is constant function on closed interval AB. So you know that if you have any constant function, its derivative must be 0. If you have any constant function, its derivative is 0. No need to say anything, right? F dash of x is equal to 0, and this is true for all x belongs to closed interval AB. You remember what is our target? Our target is to find one point. We want only one point C such that f dash of C is equal to 0. But here for each and every point of closed interval AB, we are getting derivative 0. For all points we are getting derivative 0. Actually we want 1 only. So therefore I can write implies f dash of c is equal to 0 for any c belongs to closed interval AB. If you take point C or open interval AB also, you can say actually we want point from open interval AB. Okay, so f dash of C is equal to 0. So the proof is over here for first case. Let us go to the second case. Okay, case number 2. Case number 2 is capital M is not equal to small m. That means the maximum value is different from a minimum value. Okay, so this is the second case. So here we say that at least one of capital M or small m is different from f of A and f of B. Okay, so let me write here. Then at least one of capital M or small m is different from f of A and f of B. So that means capital M is not equal to f of A and f of B, or small m is not equal to f of A and f of B. So this thing we obviously get. So let us see if it is not true, what will happen. Let us go for discuss the another case. Otherwise, so see what will happen. Otherwise, what will happen? Then you will have capital M is equal to f of A or f of B, and small m is equal to another point, right? So there is no more space to write. Make a screenshot of it. So let us discuss the second case here, remaining part of second case here. So otherwise, see what will happen if capital M or small m is not different from f of A and f of B. Let us see what will happen. Then m is equal to capital F of A and small m is equal to f of B. But we know that what is the given thing, f of A is equal to f of B. But let me write f of A is equal to f of B. This is the given part. Right? And f of A is equal to capital M. F of B is equal to small m. So if I put those values here, what will I have? Capital M is equal to small m. It is not possible because at the beginning of this case we have already mentioned capital M is not equal to small m. So therefore we get a contradiction. Actually we are discussing another case and we are again getting capital M is equal to small m. So that's why it is not possible. So therefore I will rewrite that sentence again. Therefore at least one of capital M or small m is different from f of A and f of B, right? So yes, without loss of generality we assume capital M is different from f of A and f of B. So without loss of generality we assume m is not equal to f of A and m is not equal to f of B. Okay, so let me remove this part, it is not required. So we will have some more space to write. So actually same thing we have shown in this figure. The point where the function has a maximum value, it is different from f of A and f of B. So therefore I can write implies there exists some point C, C belongs to open interval AB. Obviously it is not A and not B, C is not A and not B, so it belongs to open interval AB such that m is equal to f of C. It means f has maxima. That means function has a maximum value at x belongs to C. You know that function has a maximum value or minimum value, that means extreme value, then derivative must be 0. So implies f dash of C is equal to 0. Since, let me remind you one thing. So when you have any function f of x is equal to 0 or whatever, if you have any function, how will you find? If you have any function f of x, how will you find its maximum value? So the first condition is you always consider f dash of x is equal to 0. So this is a basic condition to find extreme value. So similarly, the function has a maxima, it has an extreme value. So that's why obviously f dash of c is equal to 0. So that's why we say there exists some point C belongs to open interval AB such that f dash of C is equal to 0. That means in both the cases we proved yes, there exists some point C belongs to open interval AB where the function has a derivative 0. Hence the result, let me clearly mention, hence the result. Okay, so in this way we completed its proof. Make a screenshot of it, then we will stop. Thank you. Bye bye.